Okay, so I'm going to talk a little bit about the systematics of oxygen isotopes, and we've had a little bit of a talk about that this morning, but I'm going to cover a few more aspects of that. I'm going to chat a little bit about the typical methodology we use for oxygen isotope collection, so that's usually via SIMS, and I'll look at some of the important aspects you need to consider about data sets you would collect, oxygen isotope data sets you collect via SIMS, because it's actually a really challenging analytical technique. You're balancing two different beams. You're balancing your primary cesium beam that's doing your sputtering against an electron beam to charge compensate. So it's a pretty difficult method. Lots of scope for things to go wrong. So we're going to look at how we can validate data. And then hopefully I get a chance to talk in a little bit more detail about some case studies where we've used oxygen isotopes to really understand a variety of processes in the crust. That's the menu. That's what I'm going to try and get through. So let's start off with some information about the oxygen isotope systematics. Why oxygen isotopes in the first place? Well, it's a very abundant element. It's the most abundant element in our solar system, and it's incorporated into a wide variety of terrestrial minerals. So it's a good signature tool that we can use to help us understand about petrogenetic processes. So what we basically do is we take an isotopic signature, typically measured within crustal material like zircon, and we can use that isotopic signature to fingerprint where the magma has been produced that gave rise to the crystal that we're measuring. It can also tell us about later alteration processes. And because oxygen isotope signatures can be distinct between fluids and the solid, we can use it to say something about fluid-rock interaction. So by using oxygen isotopes to do these various things, it's a really helpful tool to help us build up an idea of geodynamic settings. The also neat thing with oxygen isotopes is it's a useful additional tracer that can be incorporated along with geochronology, so particularly uranium-lead geochronology, but also hafnium isotopes. We can use oxygen on top of that to gain more insight. So there's three stable isotopes of oxygen, 16, 17, and 18, and it's the relative amount of these isotopes that give us a signature. So the question is, what affects the relative amount of these isotopes? And there's two main processes we need to think about that fractionate isotopes of oxygen. The two processes are kinetic fractionation and equilibrium fractionation. I'll talk a little bit about each of these. So equilibrium fractionation here is in a closed system. That's a nice bottle of Smithwick's beer. Closed system. Kinetic processes, that's usually where, well, it's where we've got an open system, so i.e. a big glass of beer with the bottle open on top. So how do these different fractionation processes actually produce different isotopic signatures? And that's what we're going to talk about now. So kinetic fractionation occurs because of the kinetic energy of the molecules basically needing to be maintained. So a heavier isotopic mass will move slower relative to a lighter isotopic mass because they need to maintain the same amount of kinetic energy under gas laws. So these are the sorts of processes that occur in biologically mediated reactions. So the lighter isotope will typically be incorporated into biological products over the heavier isotope. The diagram here is trying to convey that through some mediating process, the heavier isotope is being fractionated, it's being left behind, whereas the lighter isotope, because it's moving faster, is going to be preferentially enriched. The simple summary of that is up here, where light isotopes exhibit faster reaction rates. So light isotopic signatures tend to be associated with a greater biological mediated product. Okay, so the other way of fractionating oxygen isotopes is through an equilibrium isotope effect. And that's where heavier isotopes become enriched in compounds with stiffer bonds. Now, you'll see in the literature people say stronger bonds. That isn't actually correct. It's not stronger bonding. It's the stiffness of the bond. And that has to do with the type of bond. Is it an ionic bond or is it a covalent bond? Where there's an ionic bond, the bond stiffness is actually less. So under equilibrium conditions, in a mineral like magnetite or zircon, you can see you're getting a lighter isotopic signature compared to something like quartz. And that's because the bonding between oxygen and silicon in the quartz is stiffer. And in detail, it's more to do with the vibrational energy, where there's a reduction in vibrational energy. You get a substitution towards the heavier isotopic mass. Okay, so those are the two main processes that fractionate isotopes. But how do we actually see that in the environment? The most classic example is the water cycle, where, and we had a brief mention of this morning, where we basically are able to evaporate the lighter isotope in preference over the heavier 18. So the ratio between 16 and 18 will go towards the light isotope in the evaporation step, whereas in the precipitation step, you're more likely to drop out the heavier 18. So that's in basically a hydrological cycle, so a very geography style of process there. But similar sorts of processes and fractionations you can imagine happening in the near surface environment, of the crust as well, where you're preferentially mobilizing one of the isotopes over the other. Well, that's not good. What you would have seen there is basically the way that affects precipitation across the planet, and there is zonation within the precipitation of the planet, and that therefore affects the groundwaters. When we then look at rocks, this is probably one of the most important diagrams that you'll see, and that shows the relationship between waters, for example, meteoric waters, against either quartz or feldspar. The temperature of the process is important, and as Pete pointed out earlier in the morning, you might think fractionations would be higher under higher temperatures, but that's not right. Fractionations, the difference between these two different substances is greater at lower temperatures. And that's simply because at higher temperatures, there's more energy, so everything kind of equilibrates. At lower temperatures, less energy, the degrees of fractionation are much larger. And that means in lower temperature, near Earth's surface processes are more likely to fractionate oxygen isotopes. So when you get to higher temperatures, the signature that's in the water will equilibrate with the signature that's within the minerals, whereas at lower temperature, there will be a bigger deviation. So there's typical ranges of oxygen isotope signatures within different reservoirs within the planet, and that's helpful because we can use this as a tracking tool to help us understand the source of fluids. Those fluids being either magmas, but those fluids can also be fluids that interact with our rock mass. The reference frame normally that we think about as geologists is mantle, and the mantle, as recorded in zircon, is 5.3 plus or minus 0.6. And that signature is a signature that we tend to reference other processes to. So you can see there's a slightly larger range of heavier isotopic signatures, and that tends to be in sedimentary systems, which have had an influence of the hydrological cycle on them. Where these sediments are then reworked into continental crustal rocks through melting, you can deviate again towards heavier isotopic signatures. Lighter isotopic signatures tend to be associated with meteoric water processes and processes, for example, that might melt altered rocks, and that's more unusual in the rock record. So this is the delta notation. We've seen this multiple times today, so I'm not going to spend very long on this. So it's an expression of parts per thousand difference to a reference material, where that reference material typically is, for oxygen isotopes, is standard mean oceanic water, or Vienna standard mean oceanic water. So this gives us our delta 18O measure, and we normally refer to higher values in this reflecting a heavier isotopic signature, whereas lower values than 5.3 reflecting a lighter isotopic signature or a value submantle. Okay, so everyone's favorite mineral is going to show up here again. This is zircon, and typically we measure oxygen isotopes in zircon using SIMS, and that goes along with our uranium lead analyses. So it gives us a mechanism to understand what our uranium lead analysis might actually be reflecting. Does it reflect the primary crystallization, or has there been some other processes that might have affected the crystal? The important thing about oxygen isotopes in zircon is they have very sluggish diffusion rates. So even under quite high temperature conditions, the oxygen isotope signal is going to be pretty much set in that crystal. This is a nice example from Page, where he showed that, mapped out a grain using multiple SIM spots, and showed that there's quite a distinct difference between the core and the rim, and it's not really much of a diffusion profile. This is kind of one of the founding arguments that's been used to say that zircon oxygen isotope signatures are a useful signature of source conditions, provided we can make sure there's no later alteration effects. And checking for those later alteration effects becomes quite important, and that's something we'll spend some time discussing. All right, so moving on, that's the kind of 101. It basically has reiterated some of the stuff that you'll have heard earlier today, but from a more oxygen isotope viewpoint. So we're going to look at some the actual analytical method of collecting SIMS oxygen data, and then talk about some of the pitfalls of that approach, and some of the verification steps that we should go through. The typical in situ mechanism of collecting oxygen isotopes is via a Jamaica 1270, 1280, 1300 instrument or the like. And what we're doing is we're going to be firing a beam of cesium ions into our sample surface. So we're using the cesium gun. We're going to fire that down onto the sample surface. The sample surface will get sputtered, and that material will get transported through the rest of the instrument, being an electrostatic analyzer, which is basically sorting out all the junk that's coming off the surface, to the masses we're interested in measuring. The magnet, again, doing a mass separation job, and then a multi-collector array at this end. So we're collecting multiple isotopic masses simultaneously. And that's important because we're dealing with very small deviations. So we need to have highly precise measurements, and mass skipping, where we change the magnet sequentially to measure through those different isotopic masses, will not give us the analytical precision that we need to address the geological questions. So we're measuring simultaneously. We're also using an electron gun to flood over the sample surface to allow us to sputter from the sample surface. And that's one of the challenges of this technique, is trying to balance these two beams coming in onto that sample surface to extract material successfully off. Yeah, I don't think you need to read that. It's basic instrument conditions. The normal way this is approached is a sample standard bracketing approach, where we sequentially, through an analysis run, we measure a reference material of known value, and we also then measure our unknowns. This allows us to correct for instrument drift, because we can see through time where our reference values are plotting relative to where we know they should plot based on the true standard value. So in terms of the uncertainties then that we are left to deal with, we're left to deal with the internal precision on the measurement itself, any instrument mass fractionation, and then also any uncertainty in the reference material itself. We are typically interested, when we're analyzing zircon, in getting a primary magmatic signature to understand the magmatic petrogenesis. But there can be secondary effects that modify the oxygen isotope signal, and being able to identify when we're looking at a primary versus secondary oxygen isotope signal can be quite challenging, but there's a range of techniques. The first and most obvious technique is you could check your uranium-lead system for uranium-lead concordance. So in other words, is the grain with another isotope scheme indicating that it is acted as a closed system? But there's other ways of checking for that. One is just the zircon internal texture. Do the zircon grains themselves look like they're magmatic crystals, or is there indication of secondary processes? Is there identification of cracks and altered zones that may tell us more about a fluid rock interaction process rather than the primary magmatic crystallization oxygen isotope value? So cracks and inclusions are also bad news, and we don't want to hit those when we're carrying out our analysis. Other more subtle features, like even the pit geometry, are important to look at. So we can see here a kind of a more pristine pit. You note that they aren't exactly elliptical, and that's because with the geometry of the Kameka instruments, that's the 1270, 1280 or 1300 instruments, that the beam is coming in at quite an oblique angle. So it's coming in from the side. While this looks quite pristine, you can see this analysis has gone through a cracked area of zircon, and that has a oxygen isotope signal that looks dissimilar to the rest of the analyses. So you would start to wonder, is that a secondary signature? So having detailed images of your analytical pits is actually quite important. The other interesting thing is analysis of domains that have touched inclusions obviously show mixed oxygen isotope signals. This is a real problem because there's quite a lot of data sets that have been used to say stuff about early Earth processes that may have some of these effects undiagnosed within them. There's other instrument factors that we need to be aware of, including simply just the geometry of the way the mount has been loaded in the instrument. There seems to be a larger, I'm going to close this at the top so we can see this better. Alternately, I'm not. Basically, where the geometry of the mount has been put in with the green dot representing the unknown material, the yellow dot representing the reference material, when the material is aligned like this, we see a larger dispersion between the reference material and the standard values, whereas in an east-west orientation, that is more minimized. the point of this is you want to minimize the distance between your reference material and your unknowns. You also definitely don't want to put your analyses on the edge. The reason is that the optics of the mass spectrometer cause quite large fractionation effects simply by the lens setting of the mass spectrometer. So it would be an instrument fractionation effect, which can be variable depending on where you're analyzing on your mount surface. So you want to obviously minimize that. So having well-polished mounts with standards and reference material close to each other is an imperative to good SIMS analyses for oxygen isotopes. One way of verifying quality data is to plot instrument parameters against values for our standards, and our standards are giving the correct value. We can express how far away they are from what we expect using this instrument mass fractionation parameter. And we can see that when the lens values are within this kind of range, our standard or reference values are within an acceptable range. We can also then plot in a gray bar the range of values for our unknowns, and that gives us confidence in our standard bracketing approach. I have seen papers where the reference material values, let's say, are plotting here, but the unknown analyses are, or the range of lens values for the unknown analyses are plotting outside that range. So then you have no confidence that your standardization is working effectively. A more recent technique to try and distinguish between primary and secondary values within oxygen isotopes in zircon is to look at the OHO. So that's, in other words, the water content within our zircon. And importantly, this measure can be carried out simultaneously with our oxygen isotope analysis. So it's a very powerful tool that allows us to have some quality assurance at the same time as we're making our isotope measurement. So we're making this measurement along with our Delta 18O measurement. So our crystalline standards, Pleskovic, Tamura, BR266 and CZ3, you can see they're all nicely plotting down here, low relative amounts of water in the zircon structure, but we can see our unknown analyses are trending away from that towards heavier Delta 18O values. So these analyses would be suspect as giving us a primary value. They're much more likely telling us about secondary processes, which might be interesting for some questions, but if you're trying to get back to the magmatic petrogenesis, you wouldn't really want to use these analyses. Frequently, we see linear sorts of relationships, but they can go in both directions. So they can go both towards heavier signatures, but they can also go towards lighter signatures. And the shape of the relationship can be a mixing function as well. As a simple binary check, it's a very useful technique, but you can actually look into this in more detail to try and understand what the alteration process is. Just a final note on the analytical side is that while we are very concerned with having a flat mount surface and a good mount geometry, there can be other instrument factors that we might want to explore the effect of, and one of those could be using an off-mount reference material. Clearly, that's non-ideal, but for legacy material, that might be a real thing that you've had to deal with, where you've not been able to mount reference material along with your sample material. So what you're doing is you're analyzing your sample, then you're analyzing your reference material in a different epoxy mount, in which case there's going to be 4 components of variance within that. You're going to bring in a variance between the different sample holders that you might have used. There'll be a difference between the individual analyses runs themselves. There'll be uncertainty within the run within itself, and there'll be some other random additional uncertainty from this process. we carried out a bit of an exploration of this where we did a test between looking at Penglai zircon and BR266 zircon on a series of mounts that were mounted in different holders, and then going between each of these holders, carrying out a series of analyses and back again for several days to try and quantify the extra additional uncertainty that brings. It's quite painful. It brings in quite a lot of extra uncertainty. So it sounds awful. It sounds like you shouldn't do it. Well, you actually shouldn't. You shouldn't analyze off-mount standards for oxygen. If you have to do it, you need to propagate an extra 38% uncertainty in quadrature to account for that extra variability. Interestingly, because it's propagated in quadrature, you can still get answers that address geological questions by doing this. The end point is, if you're going to do this, try and mount your standards in your along with your unknowns. Okay, so that's kind of the background to the analytical technique. So we probably have time to discuss at least some of these case studies. How long will we go? Yeah, keep going. Right. I think I'm going to start with light oxygen isotopes because it's kind of fun stuff and a little bit more unusual. Okay, we'll do that first. We're going to go off to the Musgrave province in Central Australia. So you can see this kind of Proterozoic belt trending broadly east-west at the junction of these different Proterozoic components of of Australia. North Australian craton, South Australian craton, West Australian craton, and this is kind of sandwiched in the middle. Very long history of magmatism in this region, and including a long-lived volcanic province. Some spectacular volcanic textures, haloclastites, spherulitic rhyolites, Huame, amygdaloidal basalts, flow-banded rhyolites, and ashfall tuffs. So you've got it all there, really nicely preserved. Looking at the oxygen isotope signature of these volcanic products is interesting. And what we see is we've got this prolonged volcanic province stretching for almost 100 million years. And it's also distinctly light. So here's our mantle composition in 5.3. The oxygen isotope signature of these zircons tends to be variably light, but down to as light as 1 or 2, and that's quite unusual. The stratigraphic level against uranium lead age, again, kind of confirms this upward younging trend. But no matter what way you cut it, this is 100 million years of volcanism. It's probably the largest volcanic province on the planet in terms of both volume and age. The zircon crystals themselves are interesting. They have partially reabsorbed anticrysts, and they're overgrown by later generations of magmatic zircon. So how do we get light oxygen isotope signal into magmas? The most, well, one of the easiest ways of doing it is via caldera collapse. So we form a large volcanic system. That volcanic system grows, eventually erupts. We have shallow magma chambers, and we collapse back into that chamber near surface rocks that will have had a hydrothermal alteration system active through them for quite a while. Those rocks that are altered falling back into the chamber themselves will get remelted in a later volcanic pulse. So you get this mechanism of the volcanic system essentially eating itself and chewing through these light oxygen magmas. Why do we have such a long-lived system in Central Australia? Has been proposed simply because of the geometry of the different cratonic blocks channeling melts up to this focused area. So this makes Yellowstone look titchy. I might come back to that because that was going to be my final slide. I'll keep going. Yeah, keep going. Okay. Another area, and this time we're going to look at a mantle oxygen signal, is if we go and look at the Rural province. Now, the Rural province has been proposed to connect to the Musgraves, where we were just looking along a gravity ridge that runs from here through central Australia into Western Australia and then bends up towards the Rural province. The Rural province reflects a Proterozoic origin rooted on the Pilbara Craton itself. Looking at one of these Hafnium evolution diagrams, remember when we go upwards on this diagram, we're getting a more mantle-like signature. Where we go downwards on this diagram, we're looking at reworked crustal components. And we see magmas in the Rural province, which are kind of consistent with new mantle input into a Pilbara, an old Archean, in other words, a Pilbara Craton source. But there is this unusual young magma that's about 1.4 GA in age. I say young, it's just young for this region. And it fits within an array that is very similar to the what's seen in the Musgrave province. The Musgrave data all track back to a component that was extracted out of the mantle at about 2 GA, and Mike talked about that earlier this morning and pointed out that that widespread juvenile production in Australia between 1.9 and 2 GA. So an interesting question is, do these hafnium isotopic data simply reflect a mixture between something that is more evolved and something that is more juvenile, or do they truly reflect something that falls along this sort of evolution array? Because if they do, that fits with the Musgraves, suggesting some sort of source connection to that region. Or is this just fortuitous that they're falling in this zone simply because they're mixing, you know, this older crustal component with a new mantle component? And one way that's been suggested to address that is to use oxygen isotopes. We would predict that if this oxygen isotope, we would predict that if this evolution array back to the mantle was indeed an evolution array, not just simply a function of these mixing, we should see mantle oxygen isotope values in these grains. So let's look at the oxygen isotope composition of these analyses, and they come out at pretty close to mantle-like values. That has been used to argue that this is a true a component extracted from the mantle, roughly at about 1.9 to 2 GA, and therefore that there is some connection to other Proterozoic magmas that show a similar sort of isotopic evolution array. So that's the power of combining different isotope schemes together. Where one scheme can give us an ambiguous piece of information, we can use another scheme to fill that in and then extract further information out of the other isotope scheme. Don't really want to touch on that. Okay, so I might do one more example. So we've had an example of light oxygen isotopes from the Musgrave volcanic system. We've had an example of mantle-like oxygen isotopes at around 5.3 from the Rural province, helping us understand hafnium isotopic data. Let's now look at some heavy oxygen isotope signature. So let's go to the Pilbara Craton, your favorite, I'm sure. And it's a granite greenstone domes. So we've got these nice granite domes, we've got greenstones around them. Very spectacular map, and also the Landsat image is spectacular. What we can do is we can go and look at the magmas in this region and track their oxygen isotope composition and see what they tell us about the source history of those magmas through time. Where we start to see deviations towards heavier oxygen isotopes, that's classically interpreted as a process requiring the melting of a sedimentary component. The melting of a sedimentary component could be consistent with the idea of subduction. So where we're seeing deviations to heavier values is possibly telling us about an important geodynamic change point. This is a data set of oxygen isotopes in zircon from the Pilbara Craton, stretching from 2.5 to 4.3-ish. So we're including some, actually no, we're not. This is a global compilation in the light grays. The black squares is the Pilbara data set. So the Pilbara data set is more constrained. It's between 2.9 to 3.7. The squares in open here that are unfilled reflect secondary values. These are analyses that have abnormal OHO measurements, so these are not primary values, so we're not going to consider those as a primary magmatic signature. What we're going to look at is we can see the black analyses here seem to be all within the mantle range, and there seems to be some sort of deviation occurring at around 3.1 to 3.2 GA. That's a blow up of that area. And that has been interpreted along with some geochemistry to suggest that's when we're starting to subduct sediment in this region, causing the oxygen isotope signature to go heavy. Looking at this larger global compilation in the light gray fill, we can do some statistical analysis of that and look at the change points within it. And that's what this diagram is showing, and it basically picks up a deviation towards heavier oxygen isotope signals starting globally at 3.2-ish. So again, pointing towards that's the dawn of subduction processes, perhaps. Okay, I might just show my final slide. Okay, so summing up, basically, we've seen that we need a non-trivial analysis to get useful, meaningful data out of oxygen isotopes. We need to have some careful screening of the data, and that's really kind of helped dramatically by measuring the OHO at the same time. There's other things that we could also do afterwards. We could look at the Raman signature, for example, to understand if we're looking at a primary or secondary oxygen isotope value. We saw how we could use oxygen isotopes to distinguish a mixing array from a true mantle component within hafnium isotopes analyses, perhaps in allowing us to say something more meaningful from hafnium model ages. We saw how we could use the temporal evolution of oxygen isotopes to say something about global geodynamics, perhaps. Another important use of oxygen isotopes in zircon is looking at fluid rock interaction, and we haven't really touched on case study of that, but we can talk about that later if people are interested. And overall, oxygen isotopes in zircon are a very powerful tool to add to our isotope toolkit.